Dear students, I welcome all of you to this live class on electronic configuration of the atom of the elements and classification of the elements according to the electron configuration of the elements. According to electron configuration, the elements are classified. We will discuss in the second part. First part will complete the electron configuration of the atom of the elements. So last class we have done up to atomic number 86. So we are following the Auger principle and the Pauli's exclusion principle, and accordingly we are filling up we are writing the electron configuration of the elements. So last class we have written the electron configuration of radon 86, that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, then 4s2, 4p6, 4d10, 4f14, then 5s2, 5p6. So this is the configuration arrow. So 2 is 8, this is 18, this is 18, 32, and this is 6. So this is the configuration of the radon. So now from atomic number 87 we will write the electron configuration of the elements. So after, if you look at the Auger principle, as I have done the table last class, the electrons will be now filled up to 6s, 7s orbital. So 5p6, the electrons will filled up to 6. So we will write here, from after 86 we get francium 87, and it is we write like this as radon 86, then 7s1. So this belongs to 7th period of the periodic table in group 1A. So this francium is placed lithium, sodium, potassium, rubidium, cesium, and francium. This francium is a radioactive element. So after atomic number 82, all the elements they have high, and the N by P ratio exceeds 1, the nucleus becomes unstable. It undergoes spontaneous disintegration, emitting out the alpha, beta, and gamma radiation. So these elements are radioactive elements. So this francium is a radioactive element 7s1. Then comes 88, radium 88. So this is radon 86, 7s2. So if you look at the table which I have written last class, now the electrons will be filled up. So next element is actinium 89. Here the electron will be filled up 86. So here 5F is vacant. 5F is vacant. Now we have 5s2. Here we have 5s2, 5p6, then 5D, the 5F. Uh, 5p6, we have here, here 5p, 5, 6, 5D, 10, and here 6s2, 6p, 6. So this is the radon electron configuration 86. So this 7s1, 7s2, then 5s2, 5p6, 5d10. So this is gone. Then we will come to 6s2, 6p6, 6d1 will have 7s2, 6p6, 6p6s2, 6p6 or then 6d, and here 5f is not filled up. 5f is not filled up, 6s2, 6p6 is filled up, then 6d. So here in actinum the electron will go to 6d1. 6d1. So this is the configuration of actinum. So after actinum 89 from thorium 90 to lawrencium 103, the electrons are filled up. The electrons are filled up into 5f orbital. 5f orbital. Whereas the electron configuration, in outermost cell, what is an outermost cell? 7th cell, outermost cell, and the penultimate cell, that is the 6th cell, remains almost unchanged. Remains almost unchanged. The electrons are filled up. The electrons are filled up into f orbital of inner cell. What is that? 5f. So these elements are called as inner transition elements. These elements are called as inner transition elements. After actinum 89 from thorium 90 to lawrencium 103, the electrons are filled up into the 5f orbital, the orbital of this inner cell. What is this 5f orbital? That is the inner cell, N-2 cell. There is the N-2 cell. This is the electrons are filled up. That means you have, this is the outermost cell, it is 7th cell. Next to outermost cell is the 6th cell, and next to outermost cell is the 5th cell. So n equal to 5, n equal to 6, n equal to 7. So this is the outermost cell we call valency cell. The outermost cell we call this as the valency cell, and this is the next to outermost cell we call this as penultimate cell, and this is called the inner cell. So the electron configuration in this cell remains, the 7th cell remains almost unchanged. The electron configuration in the 7th cell remains almost unchanged. The electron configuration in the 6th cell almost unchanged, but the electrons are filled up into where? 5th cell. So then what will happen? So the chemical and physical properties of the elements generally depend upon the electron configuration in the outermost cell called as valency cell and the penultimate cell. Hence these elements as inner transition elements. And in these elements exhibit close resemblance in their physical and chemical properties. In their physical and chemical properties. Almost identical properties they exhibit. They exhibit similar type of oxidation state. They are called as F block elements. They are called as inner transition elements. And since the electrons are filled up into F orbital, they are called as F block elements. They are called as F block. They are called as F block elements. Just like lanthanides, these are also they are called as F block elements. So since there is no change in their properties, there is no periodic nature in their physical and chemical properties, so they behave like a group in a series. They behave like a group in a series. They behave like a group in a series. Hence are placed below the periodic table. They are not given space. They are not given space. Inside the periodic table, they are placed below the periodic table in a separate series. So they resemble themselves and they resemble with actinum. So these elements are called as actinides. So these elements are called as actinides. They are called as actinides. As they follow actinum, their physical and chemical properties, they exhibit their close resemblance in their physical and chemical properties, and they exhibit close resemblance in their physical and chemical properties, and also they similarity with actinum. Hence, they are called as actinides. They are called as second F block element series. They are called as second inner transition series. And these elements are otherwise called they constitute the second rare earth series of elements. Second rare earth series of elements. So all these elements are radioactive elements. So we have all these elements are radioactive elements. So we have these elements here. We have actinium 89, then comes thorium 90, then comes protactinium 891, then comes uranium 92. So all these elements right from actinium 89, thorium 90, 91, 92, all these elements, they are highly radioactive elements. All these elements are radioactive elements. They undergo constant disintegration, nuclear disintegration, emitting out alpha, beta and gamma radiation. Hence, they produce a series of, after thorium produces alpha ray, beta ray, gamma ray, so it comes thorium series. It produces similarly uranium series, similarly neptunium series. We will be reading in the periodic table and the radioactivity chapter. There we will study all these things. So those elements after, all these elements are called actinides, and those elements after uranium, all these elements are radioactive elements. All these elements are radioactive elements, and elements after uranium 92 are called as called as transuranic elements. They are called as transuranic elements. What are transuranic elements? May be a question for a student of CBSE in your 1 mark question. In the 7th period, after actinium 89, from thorium 90 to lawrencium 103, the electrons are filled up into 5f orbital. The electron configuration in their outermost cell, the 7th cell, next outermost cell, the penultimate cell, 6th cell, remains almost unchanged, and the electron configuration in the f orbital of inner cell only changes. So they exhibit close resemblance in their physical and chemical properties because of very high N by P ratio, that is neutron to proton ratio. The nuclei of all these elements are highly unstable. They undergo constant nuclear disintegration, producing alpha, beta, gamma radiation. When the nucleus emits out an alpha particle, its atomic number decreases by 2 units and atomic mass increases by 4 units. Atomic mass decreases by 4 units. When the nucleus will emit out a beta particle, in that case a new element is produced. There you will have the atomic number will remain. So in case of beta particle, they have a negative charge. So automatically the mass number will increase. The atomic number will increase in such a case. So new elements are produced. So when the new elements are produced, hence they are called, after uranium, those elements are called as transuranic elements. So in this way, our electron configurations are written. So we have done now the electron configuration of elements up to after 103. Now we come to lawrencium 103. We got here radon 86, 5f 14, 6 5f 14, 6 s2, 6p, 6 6d1. This is the configuration of lawrencium. Then comes 104 rutherfordium, RF 104 rutherfordium, and here the electron configuration is 86. Then 5f 14, then 6s2, 6p, 6 5d 6d2. So like this, the electrons are filled up to d orbital. So these elements are called as again transition elements. So now if you come to the 7th period of the periodic table, the 7th period is a fragmentary period. The 7th period is not completed. It is yet to be completed. It's a fragmentary period up to 112, atomic number 112. The elements are discovered, their electron configurations are written. So it is yet to be completed. So d orbital 10 electrons will be filled up. Then we'll come to the 60 here, then on 6d2. So here you have 7s2. 7s2. So this is 7s2. So you have left 7s2. So 7s2 is there, 6d2, 7s2. So here 7 cell is the outermost cell. They are placed in 6, 7 periodic table. All these actinides and the lanthanides, they are not given separate place in the periodic table. They are given place below the periodic table. If you go to the periodic table, you see the periodic table with you, so you will find that in the below the periodic table, so one series is there. This is called lanthanides. They are called as lanthanides. You will find in the periodic table, they are called as lanthanides. They are from cerium 58 to lutetium 71, where the electrons are filled up into 4f orbital. They are in the sixth period. But are placed below the periodic table. Now actinides, after actinum 89, so here we will find below the periodic table another stage, that is thorium 19 to lawrencium 103. The electrons are in the second period, so they are placed below the periodic table. They constitute F block of the periodic table. F block of periodic table. They are not given space. F block of periodic table. They are not given separate places in the periodic table, because in all these cases the physical and chemical properties remain almost identical. They exhibit similar type of oxidation states. Hence, they do not exhibit. They are not different from one another. Hence, they are called this. These elements are not given place inside the periodic table. They are a block of the periodic table. These are called lanthanides and actinides. And these elements are also called as the inner transition elements, because the electrons are filled up into the inner orbital of inner cell. So inner transition elements, these elements are called as inner transition elements, and they are called as the radioactive elements, because their occurrence in the earth crust is very low. They are very low, hence they are called as radioactive elements. They are called as radioactive elements, and they are called as the also inner transition elements. In your 12th class, you have this lanthanides and actinides. While discussing these lanthanides and actinides, we will be discussing in very detail. And while talking to you periodic table, soon after this class, we will start the periodic table. So there also I will be explaining you certain aspects of these F block elements. Now children, we have in some elements the electrons are filled up into s orbital. In some elements the electrons are filled up into p orbital, and in some elements the electrons are filled up into d orbital, and in some elements the electrons are filled up into f orbital. If you come to the transition elements, the outermost cell electron configuration remains almost unchanged. The electron configuration in the d orbital of penultimate cell only changes. If you come to this F block elements, you find the electron configuration in the valency cell, outermost cell remains unchanged. The electron configuration in the penultimate cell remains unchanged. Only the electron configuration in the f orbital of inner cell only changes. So these elements, they are quite different from those of the other elements. In case of in certain elements, the electrons are filled up into s orbital, outermost cell, and in certain elements, the electrons are filled up into p orbital of outermost cell. So now we will pass on to the second part of our class, that is types of elements basing on electron configuration of the elements, because the outermost cell electron configuration determines the physical and chemical properties. So depending upon the electronic configuration of the elements, it was felt necessary to classify the element. Why? Because the electron configuration decides about their physical and chemical properties. Hence, basing on the electronic configuration of the elements are classified into 4 types of elements, and that is called as S block elements, P block elements, D block elements, and F block elements. That also we'll see in our the long form of periodic table or the modern periodic table. You will observe that. Now we'll pass on to the next part of our class, that is classification of elements. Classification of elements basing on the electron configuration, electronic configuration. So this is there in your syllabus. This is there in your syllabus. So basing on the electron configuration of the elements are classified. So depending on the electrons are filled up with increase of atomic number. With increase of atomic number, the elements are classified into 4 types. There are 4 types of elements depending upon the electron configuration. So depending on the electronic configuration of the elements, they are classified into 4 types of elements. 4 types of elements. 4 types of elements. So one will come as the S block elements. Then P block elements, S block elements, P block elements, then D block elements, and F block elements. So depending on the electron configuration or the orbital to which the electrons are filled up, depending on the orbital to which the electrons are filled up with increase of atomic number, the elements are classified as S block elements, P block elements, D block elements, and F block elements. So here in S block elements and P block elements, the electron is filled up into the outermost cell. In these cases, the electrons are filled up into outermost cell. The electrons are filled up into outermost cell. So that is what to happen is happening. What it should happen, it is happening. Hence these elements are called as normal elements. They are called as normal elements. And in case of this called as transition elements, they are called as transition elements. They are called as transition elements are placed in D block of the periodic table. They are placed in the D block of the periodic table. In case of those elements, the electrons are filled up into F orbital of inner cell. That is inner cell, that is N-2F. N-2F, where the electron configuration in the outermost cell and the penultimate cell almost remains unchanged, are called as inner transition elements. These are called as inner transition elements or F block elements. So we have now S block elements, P block elements. They are called as normal elements because here the electrons are filled up into outermost cell, S orbital of outermost cell. They are called S block elements. P orbital of outermost cell, they are called as P block elements. In the atoms of those elements, the electrons are filled up into D orbital of penultimate cell. They are called as They are placed in D block of the periodic table, and they are called as transition elements, and here they are called as inner transition elements. They are called as inner transition elements. So in this way, the electrons are filled up into different, they classified into different types: S block elements, P block elements, D block elements, and F block elements. Now we'll go one by one. First we will discuss what are S block elements, and then we'll discuss what are P block elements, then D block elements, then F block elements, so that when we will discuss the periodic table, it will be very easy for us to discuss the properties, periodicity of the periodic table. Now we'll come to the what are S block elements. In the atoms of those elements, in the atoms of those elements, in the atoms of those elements, the electrons are filled up. The electrons are filled up into the s orbital of outermost cell. S orbital of outermost cell, that is ns. N is the outermost cell, principal quantum number, outermost cell. S is the orbital. So outermost cell are called as S block elements, are called as S block elements, or normal elements. They are called as S block elements or normal elements, are placed in the extreme left, in the extreme left of periodic table. In the extreme left of periodic table. So what is the capacity of an s orbital? 2 electrons. So we'll have 2 groups in the s block. So in the atoms of those elements, the electrons are filled up into s orbital of outermost cell, that is ns1 and ns2. So are called as s block elements, are normal elements, are placed in the extreme left of the periodic table, called as constituting S block. So then what is the general configuration? So the general configuration is ns1 and ns2. Their general electronic configuration is ns1 and ns2. So in all this case you will find except hydrogen, in all this case there before that there is a inert gas structure. So we will have here, there is a inert gas NH1. We will be writing the electron configuration. We will find NH1. Before that you have an inert gas. So and these elements all, what happened before that? They have an inert gas configuration. They have an inert gas configuration, and then NH1 or inert gas configuration and NS2. So the outermost cell has 1 electron. Here the beginning of the filling up of a new cell begins. So they have larger atomic size. Hence, and all these elements are highly electropositive metals. Highly electropositive metals. They are highly electropositive metals. All these elements are highly electropositive metals because they can lose this electron, they attain inert gas configuration. They can lose this electron and attain the inert gas configuration. So hence they are highly electropositive metals. So now let's write who are these elements, and they have general configuration NH1, and this is the inert gas. They have before that they have a inert gas structure. Before that they have a inert gas structure. So inert gas structure NH1, then inert gas structure NH2. Of the preceding period we will have, and wonderful way you can explain there. Now I am going to write what are these elements. Who are these elements? So they have NH1, NH2 configuration. So I'm talking to you according to children. Remember, I'm not talking to you according to modern periodic table. All the things which I am going to explain you today is according to modern periodic table. And when I will go to periodic classification elements, I will explain them in the long form of periodic table. Because why? You can understand a better manner. You can understand better manner if you go to the modern periodic table and study the electron configuration of the atom of the elements. So now we'll have that in the extreme left. We have two blocks. So as I told you, the group number, the period number is indicated by the principal quantum number. So this is 1A of the periodic table, and they have the configuration NH1, and there is NH2. This is taken A of the periodic table. They have the configuration NH2. So here N equal to 1. First period only we have hydrogen 1. The configuration is 1s1. Then second period, when we come, it is N equal to 2. It is lithium 3. Lithium 3, outermost cell configuration is 2s1. Before that you have helium, then NS2. Then comes N equal to 3. Third period, we have here the sodium 11. The outermost cell is third cell, 3s1. And before that is a neon configuration, then 3s1. Because the 2, 8, atomic number is 11, means 281. 281. So before that there is stable configuration and one electron in the outermost cell. Then fourth period N equal to 4. We have potassium 19, that is 4s1. Before this we have the argon. You can write also here as argon. Argon 18. Then you can write 4s1. Here you can write neon 10. 3s1. Here you can write helium 2. 3s1, 2s1, helium 2, 2s1. So before this you have a inert gas configuration. So this is 2s1, 3s1, 4s1. Then fifth period we will have here, fifth periodic table, N equal to 5. That is rubidium 37. Rubidium 37. It is krypton 36 and 5s1. Then we come to N equal to 6, sixth period. This is before that this is rubidium 37 and this cerium 55. We have xenon 54, 6s1. Then the seventh period will have here, seventh period of the periodic table, N equal to 7. Seventh period, this is francium 87. We have here radon 86, 7s1. So you see, in all these elements, we have one electron in the outermost cell. So this is the s block of the periodic table because the electrons are filled up into s orbital. Now if you come to this, there is no element here. Then comes after lithium, we have beryllium 4, we have here helium 2, then 2s2, then magnesium 12, we have neon 10, 3s2, then 19, we have here calcium 20, that is argon 18, 4s2, then 38 is strontium, that is krypton, 36, 5s2, then 56 is barium, that we have xenon 54, 6s2, and it is 88 is radium, that is radon 86, 7s2. So in all these elements we find the S filling up of a new cell begins with the beginning of a period. With the beginning of a period, the filling up of new cell begins. The electrons are filled up into s orbital of the outermost cell. So all these elements are highly electropositive elements. All these elements are highly electropositive elements. They constitute the S block of the periodic table. So this group 1A elements, who are there? All of them have one electron in their outermost cell. As I told you earlier, the group number indicates, but I am talking to modern periodic table, the group number indicates the number of electrons present in the outermost cell of the element. Hence, these elements are highly electropositive elements. This group 1A elements, who are they? These except hydrogen. Hydrogen is a different type of properties it exhibits. It exhibits both the properties of metal and non-metal. From lithium onwards, you will find all these elements, group 1A elements, they are called as alkali metals. They are highly electropositive metals. They are called as alkali metals. Why? They are hydroxides because they are hydroxides. The hydroxides are strongly basic and soluble in water. Forming alkalis. What is an alkali? Those bases which are soluble in water are called as bases. What are bases? The oxides and hydroxides of metals are called as bases. So these elements, the base is MOH, they will exhibit valency 1. They form the MOH, the hydroxide, MOH, the strong bases. The MOH are strong bases. They are strongly basic and they are soluble in water, hence they are called as alkali metals. And they exhibit valency 1. All these elements exhibit valency, they are monovalent. They cannot exhibit higher oxidation state. So only they exhibit +1 oxidation state. All these alkali metals, they will exhibit +1 alkali, +1 oxidation state. So these are what are, so the lithium, sodium, potassium, rubidium, cesium. And cesium is the most electropositive element of the periodic table. Many often in entrance exam comes the cesium is most electropositive element of most electron positive element of periodic table. This is the most electropositive element of the periodic table. The cesium is the most electropositive element of the periodic table. It is used to prepare the solar cells, and francium. This francium is a radioactive element. Francium is not called as an alkali metal because it is radioactive. It is a radioactive element, whereas all these elements are normal elements. So these are about S block of the periodic table, group 1A. Now let me discuss the group 2A of the periodic table. So now to come to 2A of the periodic table, I am talking about the modern periodic table. 2A, there is no element in the first period because as I told you, the period number indicates the cell number. The period number indicates the principal quantum number indicates the period number. Principal quantum number indicates the cell number. So there are two elements, hydrogen and helium. Helium is placed in the 0 group of the periodic table because its physical and chemical properties are similar to that of neon, argon, krypton, xenon, radon. So it starts with beryllium, magnesium, calcium, strontium, barium. They are normal elements. All these elements are normal elements. Barium, all these elements are normal elements. And this is a radioactive element. Which one? This radium is a radioactive element. Radium 88 is a radioactive element. So this second A, they have the general configuration NS2. Here the electrons are filled up into s orbital. The s orbital of the Valency cell is completed. In these elements, the s orbital of Valency cell is completed. And prior to that, all of them have the nearest inert gas configuration. So we know the atoms of every element have a strong tendency to lose electron or gain electron to attain nearest inert gas configuration. So these elements, they can lose these electrons and take part in chemical combination because they immediately will exhibit the inert gas configuration. So they have general configuration NS2. Before that they have inert. So they exhibit +2 oxidation state. They exhibit +2 oxidation state, or they are divalent. Their valency is 2. They are divalent. They exhibit +2 oxidation state. You can blindly write all these elements will not exhibit higher oxidation state than +2. They will not exhibit higher oxidation state. They will exhibit only +2 oxidation state. They are divalent. And all these elements are called as alkaline earth metals. They are called as alkaline earth metals. Who are they? From beryllium 4 to beryllium, this magnesium, calcium, strontium, barium. All these elements, not radium. Radium is a radioactive element. So they are the normal elements. All these elements, they are highly electropositive, and their hydroxides are alkaline. Their hydroxides are alkaline. They form their hydroxide, beryllium hydroxide, magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide, or magnesium oxide, calcium oxide, strontium oxide, and barium oxide. Their hydroxides are strongly basic and soluble in water. So their hydroxides are alkaline and they occur in earth crust. In the earth crust, they occur in the earth crust. You will find everywhere. You will find the magnesium, calcium, strontium, barium. All these elements are abundantly present in the earth. Their hydroxides are alkaline and they are abundantly present in the earth. Hence, these elements are called as alkaline earth metals. They are normal elements. So this constitutes the S block of the periodic table, and all these elements are normal elements. So this is what is the first type of elements we have discussed. They are placed in the extreme left of the periodic table, and with the elements of group 1A, the filling up of a new cell begins. So all these elements, the lithium, sodium, potassium, rubidium, cesium, they have larger atomic size than all the elements of their field. They have the larger atomic size in comparison to the atoms of the elements, other elements belong to that field. Now come to P block elements. Just I am giving the introduction of P block elements, so that next class I will discuss you the P block of the periodic table. So in the atoms of those elements, in the atoms of those elements, the electrons are filled up. The electrons are filled up. Electrons are filled up into p orbital of outermost cell. P orbital of outermost cell are called as P block elements. They are called as P block elements. They are called as P block elements, and are placed in the extreme right, of periodic table. In the extreme right of periodic table. So they have the general electron configuration. They have general electron configuration ns2, np1 to 6. They have general electron configuration ns2, np1 to 6, np1, np2, np3, np4, np5, np6, ns2, np1 to 6. All these elements are normal elements. All these elements are normal elements. All these elements are normal elements. In all this case, the group number indicates the number of electrons present in the outermost cell of atom of the element of the group number indicates the outermost cell of the atom of the elements. I am talking about the modern periodic table. In the long form of periodic table, they are called as so they are different. You will think here the group number indicates the number of electrons present in the periodic table. They have general configuration NH1 and P2. So they have NS2 NP1 in third A. So this is NS2 NP1. Then fourth A will have NS2 NP2. Then fifth A we have NS2 NP3. Sixth A we have NS2 NP4. And 7A will have NS2 NP5, and then comes zero group. Zero group we have NS2 NP6. This is the configuration. So here 3A this is a modern periodic table. If you count the long form periodic table, in the long form this is called 13, this is called fourth A is called 14, fifth A is called 15, sixth A is called 16, seventh A is 17, and zero group is 18 in the long form periodic table. But for your easy understanding, I am teaching you this. So with this, I am next class I will be completing the P block, D block, and F block of the periodic table. So it will be very better if you can come with the periodic table to the class and place while the live class is going on, so you can very well understand. And when you will go to our periodic classification of elements, it will be much easier for you to understand. And this will be also explaining you the valency, etc., the properties of the elements from the electron configuration. My dear friends, thank you very much. Those of you who have not subscribed the channel, please press the bell button and subscribe the channel so that the moment we start the class, notifications will reach you. Thank you very much.